Most of you probably know that the summation of the first n positive integers is n multiplied by n plus 1 over 2. There are different ways to prove this identity. One way to approach this is the way the great Gauss did when he was a school kid. The anecdote goes something like that Gauss's teacher in elementary school was so pissed about Gauss being able to solve all the textbook problems without any difficulty that he gave him the task of adding all the numbers from 1 to 100. The teacher thought this problem will keep him busy at least for a while. But to his great astonishment, Gauss solved this problem within a few minutes. Gauss very quickly noticed this pattern that if you add first number, that means 1, with the last number, that is 100, you get 101. Same is true when you add 2 with 99 or 3 with 98 and so on. In each of the cases, the sum is 101. As we are adding 2 terms in each of the cases to get this 101, we will have 50 of such 101, which implies the summation to be 101 multiplied by 50, which is equal to 5050. When n is an even number, it is very straightforward like this. But when n is an odd number, you have to modify the method a little bit. I will leave it as an exercise for you. Another approach is to use mathematical induction. Even though it will only work if you already know or at least can guess what is the summation. If you cannot guess the summation in advance, this method will not be effective. But in this video, I'll try to show you a simple visual proof of this identity. So without further ado, let's jump into it. To understand the proof, you have to first know a little bit about the triangular number. Triangular numbers are the numbers 1, 3, 6, 10 and so on that can be arranged in a triangular shape in the following way. Maybe some of you have noticed that these numbers are nothing other than the summation of the first few positive integers. That means we can express the summation of the first n positive integers in the triangular form with n entries in its height and n entries in its base. In this case, these entries are small circles. More specifically, if we denote the summation of the first n positive integers with s of n and the nth triangular number with t of n, then we have s of n equal to t of n. Now, consider these two triangles. Even though both of them has 8 entries in the height and the base, for the sake of deriving the generalized formula, we are going to assume that there are n entries. That means the total number of entries, in this case the number of small circles, are s of n in each of the triangles. Now we are going to do a magic. We are going to take this green triangle and combine it with the blue one to create this rectangle. The number of small circles in the column is n, but the number of small circles in the row now is n plus 1, because along with these green circles there is one extra blue circle. So the total number of entries in this rectangle is equal to n multiplied by n plus 1, which is equal to 2 multiplied by s of n, which implies that s of n equal to n multiplied by n plus 1 over 2, which is what we wanted to prove. How cool is that?